am on position at the National Polytechnic Institute of Toulouse, and with a lot of connections with the industry there, in particular the aerospace industry. I'd like to mention that the work I'm going to present is a joint work with many people, among which Dominique, who is here. Polius also have participated to some of the work, but I will summarize some of the work I did with my colleagues in the context of INF projects that were run during the last years. The idea of the talk is the following. We all know the use of event-based, the state-based method event-based, and this notion of describing the system through a state that evolves by some events and transitions. And the event-based, I used to say that it is really a method, because once you describe your model, you get for free the inductive principle that allows to check the invariance. But in the recent years, there were some criticisms about event-based, about its pool type system, which is mainly set theory, integers, and booleans, which requires to the developer to go into deep details before reaching a level of description of some data types. Therefore, there were in the late 2010 years, there were some efforts developed to define the components to allow the descriptions of theories, in particular data types, for empowering the event-based method. The interest of this data type theory, from my point of view, and this is why I will try to show today, is that you bring all what proof assistance, type-based proof assistance are powerful for to the event-based method. So my idea is to show that we should integrate both worlds in order to be able to have more powerful developments. That's the first point. The second point relates to the notion of domain and domain knowledge. When you design a system, you usually reuse some definitions that come from outside, and that's you need. And in the current version of the event-based method, you need to put this in a context and to repeat it each time you want to make this one. So I will show in this talk a generic approach that we use for describing these theories and integrating these theories into event-based. And then I will show three specific cases. One is for adding continuous behaviors to event-based for hybrid systems. The second one is to deal with ontologies of domains, in particular for critical interactive systems in aerospace industry, in cockpits in particular. And the last one relates to the meta theory of event-based, allowing to manipulate event-based by itself using the theory we have before. Okay. So we are in the context of state-based formal methods where we model complex systems, and we need to reason about and establish some properties, particular invariants, reflecting the model requirements, and we want to ensure safety properties. And by the verification of some invariants, the principle is the following: that each reachable state of the model system fulfills these invariants, and the system stays always in a safe region and never slips. Verification in the case of event-based is based on an induction principle over traces of transition systems without expressing these traces. This is the essence of the event-based method, where you have this inductive principle that reasons on just before and after state, and this is got for free once you write the model. State variables are modified by actions relying on the generalized assignment operations that is well known as the before-after predicate, and we find this in several state-based methods. So I believe that the discourse I have today applies for event-based, but I believe it applies also for this kind of formal state-based methods. For example, ISMs, raw triples, guarded command language of Dijkstra, array specification language and VBM have operations, actions in PLA, and so on, and schemas in Z. The second context elements I want to focus on is the domain knowledge. Every engineer, when he or she writes a model, has in mind some background that is something implicit in his or her mind, and provides some axioms each time he needs some hypothesis or some definitions, adds this in an empiric manner. So usually, system engineering relies on domain knowledge, which is shared and reused. All of us share, for example, the control theory, okay? And we reuse some concepts from this theory. It is formalized as theories with data types, operators, and axioms. And from these axioms and operators, we derive some theorems that we can prove independently of any usage of the design of the system. For example, we have some theorems that say that a differential equation has a solution in this condition and condition is. Okay, this is completely independent of the design mode. And we want to put this information, this knowledge, in some theories that we can reuse and borrow in our design models. We have identified in our experiments 2 types of domains. Those we call once and for all formalized domains. They are stable and reusable. Dinas Björner calls this endurance knowledge. For example, in mathematics, in physics, with flight dynamics, units, all these are well-known things, well-known information. And in general, external theories that are related to the design system. In these theories, I also put the logic that you may use in the formal modeling language. In general, you don't express it. It is implicitly encoded in the formal method you are using. But sometimes you may need more mathematical background or more logic background. You want to add probabilities, for example, and to add probabilistic logics to your system. Then you have system-dependent theories. What we call system-dependent theories are those who describe system concepts. For example, if you manipulate a human-computer interface, you want to describe what is a window, what is a radio button, what is a tick box. You want to express this and axiomatize the description of these concepts. So these are some instantiations, specializations of the above theories. For example, you want to describe the differential equations that controls an autonomous car. It is an instance of the differential equation and control theory that you have described at the higher level. So in our work, we work with valves, with tanks, with wheels, with windows, etc., to model this kind of knowledge. And we want then to borrow these domain-specific theories to our design models by bringing from these theories hypotheses that we need for establishing our proofs and some theorems that we will use as proof rules because they have been proved in that theory, and we want to use them to make new deduction to our specific model. This idea is not new. It's available in almost all the formal methods, except that we have organized it in a quite simple way in event. And before going to more details, I would like to say that in the next slides, you will see some extracts of event B code, so don't be worried about it. I will only focus on the parts that are important, just to show that this is something that is completely formalized, but it takes time and it's not as complex as my discourse may lead you to think it is. Okay, so my talk is to show how we can extend event B to handle these domain theories using the theory component of event B. The idea is to transfer and to reuse system design models, and in particular, the proofs that we do at the theory level. Because one of the claims that we have in our group is to say that making the proofs at the theory level once and for all can be done by an expert of formal methods. But asking non-experts of formal methods to do this kind of proofs is not something that helps to transfer the use of these formal methods, in particular in industry. So the idea is to say, okay, let's do the complex proofs on the theory level and allow the users, the engineers in companies, for example, to just do instantiations of theorems, simple proof rules when they do their design work. So the means, last point, we don't want to throw away the classical event. We want to integrate both of them, reuse the strategy, the techniques, the way, the method that we use on type proof assistance, and keep in mind that we still can use the invariant and the inductive process for invariant verification that we have in the. one of the means that we discovered in the last years is this notion of partial definitions. When we went back to the bibliography, we found that the first papers talking about these partial definitions came by Cliff Jones. We found a paper from '84 talking about these partial functions. Why these partial functions are important for us? Because when you define a transition, you can see it as a function that is partially defined, meaning that we only restrict this transition to the set of safe states that preserves the safe states after transition by the environment. Okay, so these partial definitions were introduced in event-B to allow free-valued logics or the definition of total functions. In fact, once your operation is well defined, this condition of well-definedness is added as a hypothesis, and you don't need to take into account these partial definitions. So in the future of my presentation, the next parts of my presentation, all the transitions, all the operations will be seen as partially defined operators. Okay, some background about event B. What is classical event B? By the way, I will not talk about refinement today, as the examples I will show do not address refinement. What is event B? You have on the left-hand side a context which is made of axioms, and from axioms you deduce theorems. These axioms may use constants and sets, and in classical B, these sets are used for typing purposes. And what is a model? A model is a set of events, a state transition system, where state variables that you have here, XA, are transformed by a before-after predicate. In these substitutions, we named becomes such that, means that XA after becomes such that this predicate holds. So it's set theory with basic types plus integers and basic types, integers, and booleans, meaning that we have a very poor type system. First order logic. Explicit state is formalized as a set of variables. It means that we have to provide the state. Initialization events and guarded events for describing this state evolution. And here you find the way we event B generates this inductive reasoning on the traces based on initialization and the set of events. And you may check invariant preservation or some properties related to variant decreasing for reachability purposes, for convergent events. And the Rodin tool set is the IDE that is associated to events. Then, by analyzing these models, there are a set of proof obligations that are described in the semantics of event, and they give the semantics of event. You have the theorem proof obligations. These are important for the next of the talk. It means that from the axioms of the context, we deduce the theorems of the context. From the invariants and the axioms, etc., of the context, we deduce the theorems of the machine. This is invariant preservation for initialization, invariant preservation for an event, meaning that if the invariant is holds before, if the transition holds, then the invariant is preserved after. Event feasibility means that these transitions can hold. There exist values that allow the transition to reach the next step, and the variant proof obligations that I will not discuss. So these proof obligations are automatically generated by the tool. And you have a set of provers, interactive provers, SMT solvers, model checkers, animators, and a set of tools that you can plug to the event to the Rodin platform, as it is an open platform, in order to check these proof obligations. So now this new component that is related to theories comes before event is not equipped with rich data types. Okay, so we don't have these data types, we don't have these operators, and we don't have the capability to describe these new data types. For example, if we want to deal with reals, we don't have a data type for real, and no continuous feature is available in native event. Okay, so what is the solution for that? shall we describe a data type for reals and continue on it? So there is no capability to add new data types except those you build through set theory, which means that you start from scratch in order to build the new data types. And there is no possibility to generate new proof obligations. When I say generate, by the tool. If you want to generate new proof obligations, you have to write by yourself some theorems corresponding to these proof obligations. And this work has to be done each time you want to apply this new proof obligation.
You don't have polymorphism, right?
In native event B, no, but in the theories, yes. Okay. So in the at the beginning of the 2000th century, Jean-Raymond Abrial, Michael Butler, and in the thesis of Issam and Mandria, they developed this new extension for supporting data types. There are two kinds of theories that can be defined. Constructive ones with constructors, which corresponds to theories where you build data types from scratch. This is very convenient. But also from the engineering point of view, something is very convenient as well, is the capability to build axiomatic theories, which means that you don't build it from constructor, you just characterize a set of axioms to build your data type. This is, for example, the approach that has been followed for reals. You can build reals in a constructive manner through, for example, the declined kites or Cauchy suites and so on, but you can also axiomatize real. This is what is used here. So the interest of this axiomatic theories from engineering point of view is that you can start your model at a given level of abstraction. This is what we do as engineers when, for example, we use some theorem from geometry without needing to make the complete proof of this theory. So there is a tool that supports this theory. How are these theories appearing in event B? You have data types with their constructors, some type parameters because of the genericity parameterization and polymorphism. You describe a set of operators. In these operators, you find two components. The definition of the operation, which is given here, for example, by expression 1. But for each operator, you have a well-definedness condition that corresponds, if those who know, for example, in PVS, this is the type checking conditions that you have, for example, in PVS. Here you have the well-definedness conditions that are associated to a given operator, and this well-definedness condition becomes a proof obligations automatically generated each time you want to apply this operator. Each time you apply the operator, this proof obligation is generated. It has to be proved, and once it is proved, it becomes a hypothesis in your model. You may also have operators that are axiomatically defined. For example, if it is not a constructive theory, you can define it axiomatically and give a set of axioms. And for the whole theory, you can also demonstrate some theorems related to the theory you have. So here, this is an extract of what the theory component is, except that I removed from this the notion of rules. There is also the capability to describe proof rules in the theory or rewrite rules. Both proof rules or rewrite rules have to be proven, okay? So they behave like theorems. This is why I removed. The interest of these proof rules is that you can add them in the tactic language of the Rodin platform once you have defined. So data types with operators and well-defined conditions. You may have constructive or axiomatic definitions. Prove some theorems. Define some proof rules. The environment is already available. The proof rules can be added in the tactic language, or you can use the theorem, the instantiation theorem, as a rule in the proof process when you use the theory. And there is a library of mathematical domain-specific theories that have been developed for reals, differential equations, etc. So, just another point about well-definedness. This is the sentence that I borrowed from Jean-Raymond's paper. What is well-definedness? It's the circumstances under which it's possible to introduce a new term So a new type element, for example, a new term symbol by means of conditional definitions in a formal theory, as if the definition were unconditional, meaning that once you have proved the well-defined this condition, the operations become unconditional, because you know that the condition holds, and then you can use it like it is a total function. It avoids describing ill-defined operators, formulas, axioms, theorems, or invariants. So how we avoid this? We avoid this by associating a well-defined proof obligation that ensures the formula is well-defined and that we can use two-valued logic. This is very important in order to stay in the single setting of first-order logic. This sub-would-be predicate is defined inductively on each formula. For example, basic event B defines these two well-definedness proof obligations. The first one for division says that a division, the expression A divided by B is well-defined if A is well-defined, B is well-defined, and B is not new. If F is a partial function, we say that the application of F to A is well-defined. If A is well-defined, F is a partial function, and A belongs to the domain of F. Okay, all this is generated automatically. These two are native for event B, but if you use the theories, your well-definedness condition become proof obligations that are automatically generated. So we will use these proof obligations. Each defined operators will be associated to well-defined conditions to ensure the correct definition. When it is applied in the theory, this condition generates proof obligations that requires the conditions to hold. And once it holds, we can use the operation as it is a total function without bothering about the condition. So the designer of the theory has to think about the right or the suited well-defined conditions. Once the PO are proved, as I said, they are added, they become hypotheses in the proof system. So if we want to define new proof obligations, it's enough to define an operator and define on top of this operator proof well-defined condition. For example, some students, to generate automatically a proof obligation, they define an operator that returns always true, means that you don't need to prove this theorem, with a well-definedness condition. So the tool automatically generates these conditions, and you will have for free a proof obligation. When an operator is defined, then the proof obligation is automatically there. So this is the setting, the formal method setting we had, and from that we can define another way of making proofs or safety proofs. So we start from the fact that state changes is viewed as a partial function in the case of non-determinism and in a deterministic transition. An invariant restricts the state changes to a set of safe states. So a well-defined partial functions starts from the safe states and goes to the set of all the states that you have. And if you want to preserve invariant, we have to check that the range of this function belongs to the set of safe states. Okay? So you can see this way of preserving invariance as a well-defined condition on a given transition. So what we are going to do later is very simple. Just say that an event, a transition in event B, triggers this operator that you have defined somewhere in the field. Okay? So we obtain an alternative approach to event B proof of invariant, which says that we define a data type for a state. Usually a system manipulates some concepts that you can associate with a data type. So you have states of type T plus operators, and to these operators we associate well-definedness conditions. And each operator of type T is associated to a well-definedness conditions, which says that these values belong to the domain of the operator, exactly as we have written it. So safe state changes are defined according to a given property, independently defined, a given property that is defined and it's independent of the model. I will show the two steps how this approach works. First step, is to define a data type corresponding to the state variable, the set of operators associated to a well-definedness condition. We define relevant theorems guaranteeing the property of the data type. And we hope that these properties that we want imply the invariant, imply the safety properties, or are exactly the safety properties. Then we formalize our model as an event-based machine, a state transition system. State variables are typed using the defined type. And in events, state variables are manipulated using operators. These state variables cannot be manipulated by any operator outside the type we have defined. This is the typing, a strong typing rule that we write with first order logic, as I will show. And then the theorems that we have, they hold for free, almost for free. I will explain to you. So let's go to show what we are going to do now. So we define a theory. This theory describes a specific property. This is what I intend. For example, I will show later that in our critical interactive system, there is a rule in the standard which says that when you make a choice on a window, this is exclusive. The pilot cannot make two choices at the same time. Okay? This is some domain property that is generic. It's completely independent from the model that you are designing. So here we define as predicates a set of properties. We define operators that manipulate the data type we have defined. These operators produce expressions or predicates on this type of arguments. I say predicates because we have designed this operator as before after, but you can have it as an expression if you want. From that, you have a well-definedness conditions for each operator and its definition. And then we say that each of these operators, when the well-definedness condition holds, imply a given property. And now you have to prove this theorem. This is the most tremendous effort that you have to do at this level. The difficulty is here. The difficulty in terms of proofs is here. But it is done once and for all. It's done on the theory, and you prove on the theory that this property is false. So the theorem must be proved, and proofs are made using the provers offered by the framework, may be done externally. For example, if you want to do it in Isabelle, as this format is something that goes straight to Isabelle locals, as I discovered with Lucas. Then what you do, you instantiate this theory. You have seen that this theory is polymorphic. It has time parameters. You can instantiate it for specific sets in an event-based model. So here I have sets S, constant C, and now my data type is instantiated by the set S, and I can rewrite the theorems of the theory on this new type parameter. And the proof of these two theorems, of these theorems, is straightforward, it's just type checking. Type checking, if the context type checks, these theorems are proved as they have been proved in the theory. And finally, we write the model. When we write the model, we have our invariant that comes from the theory, which is the property that we want to transfer to reuse from the theory. And we say that our state X is of type T of S, which is the type I have described in the type theory, in the theory. And I have added this invariant saying that every parameter and every state variable is manipulated only by the operators that I have defined on the theory. This is type checking, which is written by hand in event B because we are still in first order logic, and even if we have types, they are not as strong as what we have in other proof assistants. So once you get this, then all the state changes are recorded by invoking the operators that you have defined in the theory. And this safe theorem states that the properties hold, and this proof is straightforward. There is a tactic that has been written. Just use the instantiated theorems that we have in the previous context, plus modus ponens, which is implication elimination. 2 steps of proofs that have been encoded in a tactic. And we have applied this strategy in several cases that I will show later. But in the paper, in the proceedings, you have this approach that is completely developed and shown on the specific case of finite automata. You have a data type for finite automata, and we have made some operators related to the union, intersection, merging automata, and the property we are checking in the paper is determinism, keeping the determinism of the operation. So this is the first part of my talk, and in the next part I will show 3 cases, 3 complex cases where we have been using this approach. Are there any questions? It's okay. Okay, so let me show now 3 cases where we have used extensions of event B using this mechanism. The first one is about hybrid systems. Maybe some of you heard about this. It's the work that we have been doing with Guillaume Dupont, and he presented the paper, I think, at last iFM, not this year, but last iFM. And it's also connected to the work presented by Polius the day before the study. Then I will show the case of domain-specific modeling, which is developed in the context of critical interactive system by Ismail Mendy. And finally, the reflexive modeling with event B. And I will make some extracts of event B code. So please don't read this event B code unless I ask you. I focus on some part of it. So, okay, let's go. So now hybrid systems. What is the principle? You have a controller that is a software that controls a plant, which is described by continuous behaviors with differential equations. And there is an actuations that come from a command in order to restore the plant, and the plant is sensed, and there is this closed loop that exists between controller and no more things is needed to understand it. So discrete behaviors are okay. We understand it very well in event B, but continuous behavior requires more work. In particular, what we want to do is to show time passing and show that a variable is evolving in continuous time according or following a differential equation. So for that, we don't have a before-after predicate capable to describe this kind of thing. So we have to define an operator that manipulates this kind of variables. This is what I am going to explain. So first, we need continuous building blocks in the reals, functions, differential equations, and so on, which is a pile of theories that is not, let's say, easy to build. We have to think about it. Then we describe the continuous behaviors, and finally we integrate both of them in a model. I think, Polius, you talked about that. So, what are the continuous state variables? They are functions of time, so they go from reals, from positive reals to some values in a vector state S. And we define what we call the continuous before-after predicate. What is the continuous before-after predicate? There is a shorthand here. It says that between xt for plant, p for plant, is the state variable associated to the plant, to the continuous plant. So xt between 0 and t is the same as the previous xt. So there is no change in the past. Past is preserved. This is the first condition. The second condition says that the predicate p holds between 0 t, and now it holds between t and t prime. T prime meaning the next step, the next time step. And finally, in the new added time interval between t and t prime, we say that all the values of this time, this variable, belong to what we call an evolution domain, a safety domain H. Okay, so we can write here that the before-after predicate continuous variable xp is modified by the predicate p in the interval t and t prime. And H is a safety envelope in which the other part of time is defined. And for example, if we want to have an invariant preservation, we need to say that H intersects the invariant, and we shall be in the intersection of the invariant. This is the generic notation of this continuous before-after predicate, but there is one simple one that was used in our work, which says that instead of giving any predicate P, we give a specific predicate which says that we use the solution of a differential equation E. Okay? This predicate solution of, that is in red here, replaces this P predicate that you have here, and we have noted this with this simulation symbol saying that XP follows the solution of the differential equation E in the envelope H. So this is the way we have encoded this in event B theory, and I will show how this has been explicitly written in event B. So what are the properties of this continuous before-after predicate? First of all, it shall be well defined when the time progresses. It means that we do not go backward in time, so T prime shall be greater than T. And there is a domain coherence, meaning that for U and V, that is the complementation of the state variable, we still are in the same domain, the past still in the domain of U, and the next timestamp is in the domain of U. That's the first one. The second point is feasibility. We shall explain, we shall give only predicates for which the next state exists, meaning that the differential equation or the solution does not diverge. Okay? So this is the condition of feasibility. And the last one is invariant preservation. When you add this timestamp T prime, you shall keep preserving the invariant, meaning that the CBAP is true on the intersection H intersected by I, which is the invariant. Okay? So as you can see here, it's just characterization. I'm not saying how this differential equation converges, etc., etc. This is why I will use axiomatic theories. Finally, we start to write this with event B. We have the theory of reals, we have rings, we have functions, continuous functions, partial functions, etc. This is just an extract. We define the field, etc. For that, we define our,
For this predicate solvable or solution,
yes.
You assume implicitly that you have a kind of Hilbert choice. So if there are many, so you choose one of them.
I will give us an answer to your question, and in case it is not the right answer, I get back to you in 2 minutes. Okay. So reals, and then we define our theory of differential equations, and here you see this CBAP predicate that is defined here, and you see this SIM predicate, which is the shorthand of the CBAP on specific differential equations. It has a set of well-defined conditions. And in particular, there is one predicate which says that it is solvable, meaning that my differential equation has a solution. Okay. And the second point, the result of this predicate is the solution of the differential equation, of the differential equation. And now I have to add some conditions ensuring the solvability. This is my
a solution or the solution?
Sorry?
A solution or the
solution? A solution. And one example of solvability conditions that we are using is the Cauchy-Lipschitz theorem. Cauchy-Lipschitz is a theorem that under conditions ensures that the differential equation has a solution. So this theorem is described under the banner of Axioms. So we don't prove it. Now you can say, okay, Yamine, why don't you prove this? Okay, let's go and develop a theory to prove this theorem. This is why I said we are using this at an axiomatic level, and this depends on the level of formality we want to reach. Okay? And there is an important theorem here that is very important for proving the models, which says that on the small interval of time t and prime will preserve the invariant. The C bar preserves the invariant. This theorem is true, and it will be used as a proof rule for the model. So the answer to the question is here. So we can enumerate a set of conditions, set of theorems on which we can make some conditions for solvability. But again, this theorem is not proved here. Okay. Once we have done this, we can write models. So what are the models now? We can declare time, discrete variables for the controller, and plant variables for the plant. These are typed like this. So the discrete variables are states. The plant is a function from reals to the state S. And then we can define a set of events, sensing event, which gets an information from the plant under a condition, which is P, the predicate. We can make actuation. What is actuation? Under some conditions, we can say, okay, now we are braking. The car is braking. The car is accelerating. So you change the differential equations that steers the plant under a set of conditions that you have. Here you have a generic model. This model is instantiated by refinement. So you instantiate the set states, all the parameters that you have here are given as witnesses for some conditions. And there are several case studies that have been developed using this theory. And the talk of Paulius the day before yesterday is one particular case of refinement of this applied to railways. Okay, that's for hybrid systems. Then we I moved to a second example related to critical interactive systems. Here, what we have been doing, we were working with people from aerospace industry. They always talk about standards. When you write a model, they say, yeah, but according to the standards, you cannot do this, but according to the standard, you can do this, etc. They have a lot of requirements that come from the standard, which makes very complex to build the model. Each time we have to revise our model. So we decided to write some standards as a theory, meaning that we describe the types of standard. So the designer must conform to standards, this is what I said. And we took this RNC 661 standard, which describes cockpit display systems and standard protocols to make aircraft systems to communicate. It is well known in industry. It's used for many aircrafts. 800 pages of definitions. In our work, we focused on chapter 3 of this standard, and we have developed Ismail has developed some case studies, the weather radar system, traffic collision avoidance system, TCAS, etc. But from the human-computer interface went on. So what we did, we first had to think what is the language to describe these standards. So we went through the literature and what is done. We found that a lot of people are using ontologies to model these standards. So we decided to define an ontology in event-based. But we don't have an ontology modeling language. How do we write these ontologies in event? This is why we went again to a higher level and we describe the theory for ontologies. So we have an ontology theory, which is a very simple one with just classes, properties, and instances. So we have a type parameters C, P, and Y, and we describe the set of constructors for our data type, classes, properties, and instances. We associate properties to classes. We associate instances to classes. We describe class associations between a class, property, and the class, and so on. This is not complete. It has to be enriched in case we want something that covers languages like all or any other ontology modeling language. So this ontology theory led to 37 operators just for those we needed we did not care about completeness for the moment, but this is an issue that we will have to address. So this is again an extract of what is the theory of ontologies. For example, you can get the instance of an association. You can check if an ontology is well built. You can check if a subset of instances belong to a given ontology or not. So there are a set of operators that have been described. Theorems as well have been described. For example, this theorem says that there is a relationship is transitive. Okay, so to prove this theorem, we had to prove set inclusion. It was not too complex, but this is the example of the theorems that we need to prove. And there is another one which comes about the closure of the is a relationship in order to compute kind of subsumption, etc. Okay, then comes the RN 661 theory. I don't want you to read this. 54 operators, 17 axioms, just for chapter 3, and we are not sure that we did the right formalization. I will get back to this in my conclusion. So we have some constants. We can select radio button, radio box. We can define colors, a lot of labels, buttons, etc. All the elements that we have in our standard. Then some axioms, very complex axioms about the conditions and the properties that you have in the standard. And finally, we applied this for a case study. This is a weather radar system. And the property we have to, in fact, what the pilot is doing, the pilot selects a mob, and he also selects an angle for the radar in the plane. And this is only one application. There are two others on the same critical interface. And one of the properties that is very important for the certification purpose is to check that only one widget here is triggered. Okay, so the properties are these ones. The selection of the check button must be exclusive. You cannot select the check button and something else. And the title angle must be in a specific range that you have to choose here. Okay, and from that, we did the same work as in the beginning of my talk. So we declare a variable that is a user interface, belongs to an ontology. It's an instance of an ontology. Okay, and there are some properties that are true. In particular, the exclusivity. You see here the consequence that B1 equals to B2 means that there are not two B1s that are different. You have it here, and for the title angle value, you check that the value of the title angle is in the right set. Okay, but here you can ask, did you model the right set of values of the title angle? And here you are right. This is problem of theory validations that we did not address in this way. Okay, so then from that, you write a model and you can change the title angle or change the mode selection by calling operators from the standard. And for free, these operators preserves the theorems that you have written in the standard. Last example is the case of manipulating event B by itself. This is close, Marie, to what you have been doing, for example, with institutions. So here, what we want to, this requirement came from the fact that we wanted to add new proof obligations. For example, if I want to add deadlock freeness of my events, I have to write by myself the theorem which says that there is a disjunction of the graphs. Okay. For example, we had a question from people from human-computer interface. They say, for example, we want to check that every input event where a user enters a value is followed by a confirmation. So we want to check that this property comes from standard. Every acquisition, every input, every sensitive value by interface must be followed by confirmation. The pilot shall confirm what he has been entered. So these kind of properties, we want to inject them directly to the event method without having to write the theorem each time for this specific operator. So what we did, again, this is classical in type theory, but it's, I think, original in event field. We wrote a theory which contains type parameters, which are states and events. And to encode this machine that you have here, we have written this theory. And this theory has two type parameters, state and events. What is a machine? A machine is built with this constructor with an init event, a set of progress events, an after predicate for the initialization, a before after predicate for an event, a guard for an event, an invariant, etc., etc. So this is the way you build the machine. So now we have a theory on machine. We can write some operators, in particular an operator that checks that the machine is well built from structural and static point of view. For example, here, you say that the events are well constructed if events are partitioned as an initialization event and a progress event. Okay? And from that, you add some proof obligations, some theorems, which are predicates here, saying that a machine is well constructed if the before-after predicate is well constructed, the guard is well constructed, the events are well constructed, the events are well tagged, the variants are well constructed, etc., etc. This is just for structural point of view for the moment. Then we have to deal with proof obligations. How shall we generate and write these proof obligations? Again, we write an operator for that, since we are able now to manipulate the states. So if I take the proof obligations for invariants, each proof obligation is described as the following. The invariant is preserved by initialization. If the invariant holds before, it holds after, then the invariant is satisfied by the machine. So three operators for initialization, for one single event, and for the final inductive event. So what we have, initialization must preserve the invariant. Here you have machine init predicate, which takes that the machine preserves the after predicates preserves the invariant. One event preserves the before after, one event with before after predicate preserves the invariant. You have a well-definedness conditions which say that it must be a progress event and not the initialization event. And then you say that the invariant intersected with the guard is included in the invariant for the next step after applying the before-after predicate. So what is tricky here is that we are using set theory. That's the event here. So once we did it on one event, we generalize it for all the events, saying that for all the progress events, we have machine, the invariant is true at the initialization, and for all the progress events, we have each event fulfills the invariant. So now we have three operators, and we are capable to write the proof obligation associated to the invariant. And in the same manner, following the same technique, which is inductive, initialization, progress event, and generalization, we wrote it for invariants, theorems, feasibility, natural variant, progress, etc. And if we want to add a new proof obligation, just add an operator here. This is what we did for 2 or 3 other proof obligations. You can see this in the other papers we have written. Finally, the proof obligation is generated either by a well-definedness condition or by pushing the proof obligation, which is a predicate, this operator is predicate, pushing it as a theorem in the machine. Finally, when you want to use this, then you have to make the instantiation of this theory. There are 2 cases of instantiations, but before I have to mention that we also have proved the correctness of the invariant on traces. It means that we have a theory of traces that is defined sequences, and we show that each event preserves the invariant. So 2 cases of instantiation. One is deep instantiation. It means that we produce a context, meaning that a machine becomes a first-order logic formula expressed in set theory. Or we use refinement of ad hoc machine in the way it is done in TLA. I will go very quickly on this. So if we have a deep modeling, what is a machine now? A machine is just valuation of the sets, okay? And if you want to prove that your machine is correct, you just use the operator, the predicate operator that we have defined as a theorem. The second one consists in refining this machine. What is this machine? It has two events. One is initialization and one is progress. So each time I want to instantiate my machine, I refine the init event and I refine the progress event as much times as I have events in my own machine. So just to conclude, this is a framework that integrates both event-based model with its built-in induction principle. I think it's very important to keep it, and I think that in the cases I showed, we kept this capability of cutting the proofs thanks to the definition of the machine and events, plus type theory, and reaching the type theory that is provided by the theory component. So we can now enrich event-based modeling with data types. Well-definedness conditions proved very useful for proof obligation generation. We can outsource complex proofs in the theory, since many of the proofs that are a little bit complex are done on the theory side and once and for all. And we can reuse these theorems as proof rules or as rules that we use in the models to reduce the proof effort. However, still a lot of work to do. More formalized domain theory are required. How do we organize this? We need a library, maybe something to be standardized in the case of some engineering ontologies. The consistency of the defined theory is a problem. It is not yet addressed. I think I discussed, for example, with Michael Löschel, maybe Probe can help to find witnesses to the axioms for guaranteeing the consistency of the theory. For the moment, our theories are just checked by reading. The second point is to build the bridge with between event-based theories and other proof assistants, because many theories have been developed in type theory, proof assistants, and we do not have yet, at that time, we don't have the way to translate it directly to set theory and context. But with this intermediate level of data type that is offered by theories, I think we can succeed to do it. And last, an engineering process. What is the right granularity for axiomatic theories? For example, do I need to prove this Cauchy-Lipschitz theorem in my models or not? Or shall I use it as an axiom? So what is the level of abstraction or granularity that I need for my axiomatic theory? For example, I know that in Paris, Sylvie Boldo has built a complete theory for reals and control theory that starts from scratch, but it's a huge effort and it's difficult to be reused. I think this is something that we have to think about it, and maybe many other ideas that you may suggest or you may work on. Thank you very much.